Alright folks, so in this tutorial we are going to learn how to prove the legitimate condition of a Poisson distribution. Now a random variable x is set to follow a Poisson distribution with parameter lambda, where lambda is greater than 0. Okay, so take note of this. Lambda is always greater than 0. Now let's look at the PMF of a Poisson distribution. The probability of x is equal to x, which is equal to lambda to the power x e to the power minus lambda on x factorial, where x lies between 0 and infinity. So take note that in a Poisson distribution, the values of x lies between 0 and infinity. So for legitimacy, there are two conditions that we would have to satisfy. So one, we would have to prove that probability of x is equal to x is greater or equal to 0 for all values of x. And two, we would have to prove that if you should sum the PMF from 0 to infinity, the end result should be 1. So these are the two conditions that we would want to prove in order for us to establish the legitimate condition of a Poisson distribution. Now let's start with the first one. So we want to show that P of x is greater or equal to 0 for all values of x. Now to do this, we are going to employ what we call the Maclaurin series. Okay. So now let's look at the Maclaurin series. So Maclaurin series states that if you sum from 0 to infinity and lambda to the power x on x factorial, you should end up getting e to the power lambda. Okay, where e is equal to e to the power lambda is equal to 1 plus lambda to the power 2 on 2 factorial plus lambda to the power 3 on 3 factorial plus till you get to infinity. Alright, so kindly take note of this, the Maclaurin series. This is what we are going to use throughout this tutorial. Okay, so with the Maclaurin series in mind, let us now prove that the probability of x is equal to x is greater or equal to 0 for all values of x. Okay, so this means that if you should substitute any of the x values, the end result should be either equal to 0 or greater than 0. Okay, so it means that there's no way you should substitute any value of x and get a negative. That's what it means. Okay, so and also you must make sure that the values you get should lie between 0 and 1 because you are calculating probabilities. Okay, alright, so let's note that if we should sum, let's look at this, the sum of lambda to the power x e to the power minus lambda on x factorial can be written as e to the power minus lambda out because it's a constant So we factored it out because we are summing on x, so anything without an x is treated as a constant. So we can actually write this way. Now if you realize, this is actually the Maclaurin series that we are talking about. Can you identify that? Okay, so this is the Maclaurin series that we are talking about. Okay, so let's go back to the Maclaurin series, which states that if you sum from 0 to infinity e to the power x on x factorial, should get 1 plus lambda squared on 2 factorial plus lambda to the power 3 factorial plus till you get to infinity. Okay, so this simply means that if you should substitute 0, you should get 1. Substitute 1, you should get lambda. 2, you should get this. 3, you should get this, till you get to infinity. Okay, so now let's try and find p of x is equal to 0 from our PMF. So this means that we are going to get lambda to the power minus e to the power minus lambda, and we are going to substitute 0 here. Let me make it simple. So in this case we are substituting 0. Okay, so we put 1 here, this one, and we end up getting e to the power minus lambda, which is actually greater or equal to 0 because lambda is greater than 0. Okay, now if you substitute 1, you end up getting e to the power minus lambda, and so if you substitute 1, you're supposed to get this lambda. So lambda e to the power lambda, which is also actually greater or equal to 0. You can actually check. Now let's continue. Now let's substitute 2. So p of x is equal to 2 will be equal to by e to the power 2 2 factorial, which is clearly greater or equal to 0. If you substitute 3, you should also get a value which is greater or equal to 0. So it implies that if you substitute any of the values of x to get to infinity, you should get an answer which is greater or equal to 0. So clearly we've been able to prove that p of x is equal to x is greater or equal to 0 for all values of x. This means that if you put any of the values of x into the PMF function, you get a value which is either greater or equal to 0. So there's no way you will get a negative value when you substitute the range of values which runs from 0 to infinity in a Poisson distribution. Now let's go to condition 2. Condition 2 states that if you sum the PMF from 0 to infinity, you should end up getting 1 for all values of x. Okay. Let me write it this way. For values of x lying between 0 and infinity. So now let's do the summation. Okay, So this implies that we can actually write what we have here. So our aim is to write it so that we can actually get a Maclaurin out of it. So let's factor e to the power lambda out, because it's without an x, so it's treated as a constant. Okay, so now watch this. Do you see the Maclaurin series? Alright, so I hope you can all see the Maclaurin series clearly stated here. Okay, so now it means we've been able to express this in terms of a Maclaurin series. Okay, that's fine. Let's continue. Now let's revisit the Maclaurin series. It stated that if you should sum from 0 to infinity lambda to the power x on x factorial, you should get e to the power lambda. Okay, so it implies that now summing from 0 to infinity e to the power x lambda to the power x factorial e to the power minus lambda should give us e to the power negative lambda times e to the power lambda. So now this implies that we can write this whole expression as e. Because they have the same base, you can actually add their exponents. Okay, we end up getting e to the power 0. Okay, so this implies that summing from 0 to infinity on this PMF is equal to e to the power 0. Now e to the power 0, folks, is 1. Okay, so it means that we've been able to prove that summing from 0 to infinity over this PMF is actually equal to 1. So it means that we've been able to establish the two required conditions. So one, we've been able to establish that p of x is equal to x is greater or equal to 0 for all values of x. And 2, summing from 0 to infinity on the PMF is also equal to 1, where x lies between 0 and infinity. Well, I hope this video was helpful. Can you do well to like and share our videos, and don't forget to subscribe. And after subscribing, do not forget to also press on the bell icon so that you don't miss any new updates from Co-Prime Statistics. Thank you very much.